Alright, welcome back to another video on my channel, my_exe. Today we're going to look at possibly some people would say a unrelated subject to perimeter and area, which is the Pythagorean theorem. And this is the one of the most fundamental theorems that are used in some researches and stuff like that. But also it is applied to in real life, to constructing house and calculate the coordinates of GPS stuff and things like that. So I decided it's pretty interesting to put this in the video. I mean the playlist. So the Pythagorean theorem is as so. So assume we have a right angle triangle with side lengths A, B, and C, where C is the hypotenuse, which is the longest side in the right angle triangle. A in this picture shows the base of the triangle. B shows the height of the triangle, or some people would say altitude. Then it follows that A squared plus B squared plus C equals C squared. And there are some proofs that you can find in the internet. Some uses rearrangement of these copies of triangles. Some uses the similarities of triangles, and then you can just work out from that. And maybe you can just work out your proof by your own and see what you have. Alright, the converse of the Pythagorean theorem states the same. And what I mean by the converse of the Pythagorean theorem is instead you're given that the triangle is a right angle triangle. You're given that the sides of a random triangle are A, B, and C. Just the exact copy, but however, we don't know whether this is a right angle. Maybe it is, maybe it's not. And in some questions, people would label it not to scale to make sure that they won't just say, oh, it looks like a right angle, therefore the triangle is a right angle triangle. So the converse of this theorem states as so. So if the side lengths satisfy that A squared plus B squared, where A and B are the smaller sides, keep in mind that, equals C squared, which is the length of the largest side of this triangle. If these sides satisfy this formula, then it is in fact a right angle triangle. And what I'm afraid for some students that are learning the Pythagorean theorem at first is they often confuse which one is A, B, and C. Although some commonly mistaken C with the other two sides. So here's how I would explain this. So C is the hypotenuse. So C is the hypotenuse, which means it is the longest side. And assume you're given this exact same picture right here, and before you plug in just the random sides into the formula, you must defer which one is the hypotenuse, which one is the base, or which one is the altitude. Well, it's okay to differ between the base and the altitude depending on which perspective you're looking at. However, keep in mind that C is the most important one, which is the longest side or the hypotenuse of this triangle. And yeah, so that's it for this explanation. Let's jump into
Alright, so question
1. This figure shows a semicircle, and keep in mind I'm also talking about things related to perimeter and area that uses the Pythagorean theorem. So this figure shows a semicircle inscribed in a trapezium, and using pi equals 3.14 and giving your answer square to the nearest integer, find the perimeter and area of the shaded figure. And I haven't shaded it yet, but it is this area right here in red. So let's start off with perimeter. So the perimeter of this shaded area is the sum of all sides that make this figure, which is 24 centimeters plus 15 centimeters plus whatever the length of this arc is plus whatever the length of this side is. And first, it's probably obvious to find out the length of the arc. Notice that the length of the arc is the length of the arc of a semicircle, which is, I'm just call this P of arc right here, is equal to a half times the circumference of the circle that was originally built into this. So if a half times 3.14 times the diameter, which is 16 centimeters. And you can just calculate this, and you just get that this will be equal to 25.12 centimeters. And for the length of this side right here, well, we can just use the Pythagorean Theorem by first setting up the right angle triangle. So we can just move forward this height of this trapezium into this thing right here, this dashed line, and keep in mind the length of this dashed line will be still the same, 15 centimeters. And then next, we're going to find this length right here, which is pretty simple. It's just 24 centimeters minus 16 centimeters, which is 8 centimeters. And using the Pythagorean Theorem, you get that this length, well, using the Pythagorean Theorem first, let's just suppose this length is x. So we have x squared equals the sum of the squares of the other two sides. This will be equal to 289 centimeters squared, and x will be equal to, and we're just going to take the positive value because we're in the world that we're going to suppose that all distances are positive. So this will be equal to positive 17 centimeters. So this x will be just replaced with 17 centimeters. And now we're ready to calculate the perimeter, which is just the sum of the sides and arcs. So let's see, we have the total perimeter is equal to, let's see, we're just going to count from this side right here. It's 24 centimeters to 17 centimeters and so on. So we have 24 centimeters plus 17 centimeters plus the length of this arc, which is 25.12 centimeters plus 15 centimeters. And calculating this, you get this will be equal to 81.12. However, let's just round that to the nearest integer, which is 81 centimeters. Nearest integer, and I put z down for integer. Alright, so that's the perimeter. Now for the area, well, notice first that the area of this weird shape right here is just actually the area of the trapezium minus the area of the small semicircle. Now we know that the formula for the area of the trapezium is just the average of the parallel lines, which is a half times in parentheses 16 centimeters plus 24 centimeters times the height, which is 15 centimeters in this case, minus the area of the semicircle, which is half the area of the circle that was built into this. So this will be equal to a half times 16 plus 24 is 40 centimeters times 15 centimeters. And this will be a, oops, this will be a half times 3.14 using pi. And then the radius is the half of the diameter in this case, which is 8 centimeters. And I'll let you guys continue this step, and what you end up is 199.52 centimeters squared, which after we're going to round this to the nearest integer will be 200 centimeters squared. So those are the answers for question number 1. And for question 2, these figures shows different squares with different shapes with different dimensions. So the one in back is a rectangle, and this is a typo. So the one in back is a rectangle with side lengths 48 centimeters and 24 centimeters. The one in red is a square with side length 6 centimeters, and the one in blue is a right angle triangle with the height of 8 centimeters and the hypotenuse of 10 centimeters. How many squares and triangles that you can cut off from the bigger rectangle without any remaining pieces? So let's just calculate first how many squares we can cut from this. So to do this, I'm just call this n of square, where n of square represents the number of squares that you can cut out from this, which is just the area of the bigger rectangle divided by the area of a square, a single square. So the area of the rectangle will be 48 centimeters times 24 centimeters, while the area of the square will be 6 centimeters squared. And you'll get this will be equal to 32. So therefore you can just cut 32 squares with side lengths 6 centimeters from this bigger rectangle. So that's basically it. Alright, for the number of triangles, we're just going to do a little bit of work first. I'm just going to draw a upscaled version of this triangle with the exact same dimensions. So notice that 10 centimeters is the hypotenuse and 8 centimeters is the height. So you can just use the Pythagorean Theorem, knowing that this is a right angle triangle from the question, to find this length right here. And we just count this length first, x. So we can just form an equation in terms of x, as shown. 10 centimeters squared is equal to 8 centimeters squared plus x squared. Simplifying this, and do some simple stuff. We can just subtract 64 centimeters squared from both sides, and then afterwards you can just take the square root. So x would be 6 centimeters, taking the positive value. So we can just replace this x with 6 centimeters. And we're not going to use this 10 centimeters anymore, so we can just erase that, because what we're going to do is to calculate the area as using the same strategy as we've done above. So in this case, the number of triangles that you can just cut out from the bigger rectangle will be the area of still the big rectangle all over, in this case, the area of each triangle, or I would say a single triangle. So we have 48 centimeters times 24 centimeters all over the formula for a area of a triangle will be half times 6 centimeters times 8 centimeters. You can just cancel some stuff from here. You get 48. Alright, so you can get 48 triangles from this bigger rectangle. Alright, for question 3, this figure below shows a right angle triangle inscribed in a semicircle. Using pi equals 3.142 and giving your answers correct to one decimal place, find the perimeter and area of the shaded area right here. So I'll start off with perimeter. So first, notice that the triangle here is a right angle triangle. Therefore, we can just use the Pythagorean theorem to calculate this length right here. And notice that this length here is the longest side, and we can just see that by, well, it's pretty easy to see if you extend these. If you compare this length to the other pieces of these sides, this one is pretty larger than the others. So I will let you guys calculate this length right here, and what you get is this will be equal to 15 centimeters. Alright, and with this we can just calculate the perimeter of the shaded area, which is this length right here, 12 centimeters, plus this length right here, plus this arc right here. And we can just calculate this arc here very, very easily. So I'm just calling perimeter of arc is equal to, well, it's just the half of the circumference of the circle that was originally built into this. And the diameter will, well, just write the formula first. So this will be a half times pi, and we take the approximation to be 3.142 times the diameter, which is 15 centimeters. And you can just calculate this, and this will be equal to 23.565 centimeters. And therefore the total perimeter of this will be as shown. So it's the length of the arc plus the length of the other sides right here, which are 9 centimeters and 12 centimeters respectively. And you simply get this is equal to 44.565 centimeters, and approximating this correct to one decimal place, you'll get 44.6 centimeters. Alright, so that's the perimeter. Now we're ready to work out the area. Alright, so if you haven't noticed already, the area of this shape right here is equal to the area of the semicircle minus the area of the right angle triangle. Alright, so the area of the semicircle is just a half times pi times the radius of the semicircle, and the area of the right angle triangle will be a half times base times height. I'm just going to write the formulas first, and this will be equal to a half times 3.142 times the radius, in this case is half the diameter, which is 7.5 centimeters squared. And the reason I'm choosing decimals for this is since pi, the approximation for pi is a decimal, and the length of the diameter and the radius is both not divisible by 7. We're just going to use decimals for this, since we can just input this to a calculator or just calculate it manually if you're brave enough to. So anyways, the base and height of the triangle will be 9 centimeters and 12 centimeters. And I'll let you guys continue this calculation, and what you'll get is equal to 34.36875 centimeters squared. Correct to one decimal place will be 34.4 centimeters squared. Alright, so that's it for question 3. Let's jump into question 4. Alright, for the fourth and last question, this figure below shows trapezium ADEF, rectangle ABEF, and triangles BCE and CDE. The area of trapezium ADEF is 180 centimeters squared. Find the lengths of AF, CE, and DE. So first, let's just work out the length of AF. So I'm going to first assume that the length of AF will be h for height, because why not? And since we know that ABAF is a rectangle, this length is also 6 centimeters, because opposite sides are equal. And since these line segments are also equal to 6 centimeters, therefore the whole segment of AD will be 18 centimeters. Right, with this information we can just form an equation in terms of h relating the area of this trapezium. So the area of the trapezium is a half times the sum of the parallel lines, which are 6 centimeters and 18 centimeters, times 8, which is the height, is equal to 180 centimeters squared, as said in the problem. So you get this is equal to 12 h centimeters equal to 180 centimeters squared. Therefore h is equal to 15 centimeters. So in fact the length of AF is 15 centimeters. Alright, so let's work things out for length CE and DE. So for length CE, I'm just going to focus on triangle BCE. And since we know h is 15 centimeters from the last part, this line right here is also 15 centimeters. And we also know this length is 6 centimeters, therefore we can just simply calculate the length of CE using the Pythagorean Theorem, which is, we know that C is the hypotenuse, this is the longest side, which is C squared is equal to 6 centimeters squared plus 15 centimeters squared. This will be 36 centimeters squared plus 425 centimeters squared. Adding this, you'll get 261 centimeters squared. And taking the square root of both sides, CE is equal to the square root of 261 centimeters. Or if you just want to try to factor it out, do whatever you want. I'm just going to factor out a 9 from this, so it will be 9 times 29 centimeters, and we can just take the square root respectively because the insides are both positive. Therefore we have 3 times square root of 39 centimeters. And if you input this to a calculator, you'll get this is roughly equal to 16.1554944 so on centimeters. Alright, so that's the length of CE. Let's work out length DE. So for length DE, I'm just going to look at triangle BDE, it is also a right angle triangle. So let's just redraw that. You know, this length from our previous picture is 6 centimeters by 6 centimeters, which is equal to 12 centimeters. The length of BE is 15 centimeters. Alright, so we can just calculate the length DE using the Pythagorean Theorem once again. This will be 144 centimeters squared. This will be 369 centimeters squared. That means DE will be the square root of 369 centimeters. Or I would probably just factor out a 3 out of this. I mean a 9 from this, but later on it will be 3 outside. So we have 9 times 41. Taking the square root separately, you got this will be equal to 3 times square root of 41 centimeters. And if you input this to a calculator, you'll get this is roughly equal to 19.2093727 so on centimeters. Alright, so if you compare which side is longer, it's obviously DE because of our calculations and approximation by using the calculator. However, you can just quickly notice that using the Pythagorean theorem, or by just looking at the diagram right here, the height will be still the same in both triangles. However, the bases are different, and one is 6 centimeters, one is double, which is 12 centimeters, and obviously the bigger triangle we have the bigger hypotenuse. So that's how you find which side is bigger without actually calculating it. So that's finish this question 4 as well as this video. So hopefully you guys enjoyed this. Please subscribe for more, and I'll see you guys in the next one.